Hello, everyone. Welcome to this episode. And today I'm going to be going over the Raspberry Pi RP2040 chip. So, just a second while I share my slides. So, to get started, the RP2040 is a chip from Raspberry Pi and it implements the ARM Cortex M0 Plus processor. The instance of the RP2040 comes with a dual core, and what that means is you're able to multi-thread in your code. I have on the screen the spec sheet for the RP2040, and it comes with a lot of things. It runs at 133 megahertz, and that's per core. You've got 264 kilobytes of on-chip RAM, which is quite a lot for microcontrollers. And you've got a lot of communication options. You've got UART, which is serial. You've got SPI, you've got I2C, and you've got pulse width modulation. And all of these are implemented on various um, I/O ports as they are exposed from the RP2040. You've also got an onboard USB controller. What that means is when you take the chip itself and you implement it in your own um, PCB, you do not need a separate controller for USB. And that is something that some people have to implement if they're using some alternative chips. There's also something called Programmable Io. It's a bit of an advanced topic, but what it does is it gives you 8 state machines that you're able to do something that is called bit banging. And bit banging is for controlling some things that require a lot of, let's say, binary bits to show state. So think of it like controlling a really long LED strip. Then bit banging is something that is required for that. And these state machines run independent of your two cores. So you're able to get a lot done with Programmable IO without slowing down your core application. And there's also the supported input power range, which is 1.8 volts to 5.5 volts. And it has a good operating temperature, so you're able to put it in some embedded locations and still get maximum utility out of it. It's low power. It's actually designed for embedded applications like wearables in healthcare. So there's 3 low power modes that are available on that processor. It also has a clock in it, so you don't need a separate crystal oscillator, for example. There's an onboard temperature sensor. Um, this particular one is optimized for integer arithmetic. Now, in terms of the optimizations, it's 32-bit reduced instruction set computing at 133 megahertz. And so what that means is that you have able to do a lot more than you would with the traditional 8-bit RISC processors. 32-bit will take 4 times as many instructions and run them in one clock cycle. Again, this is optimized for integer arithmetic. It's also optimized for machine learning on the chip. It's multilingual, so you can do C and C++, you can do MicroPython, you can do assembly language. And then there are also examples of other languages that have been ported for it. So I've seen examples in BASIC, in Rust, probably 10 other languages. again, low power modes. Something else called direct memory access. And what direct memory access does is it offloads reading and writing memory locations from the processor cores. And this is useful when you have to do something like reading accelerometer data, for example, and processing it. In some implementations, that act of reading the accelerometer data consumes your processor cores. In this case, with direct memory access, you can just have a thread that reads your accelerometer data and writes it straight into memory, bypassing your processor cores. So in essence, you're able to do a whole lot with the RP2040 without consuming processor time. A little bit technical, but this is what the pipeline looks like if you're interested. And I will share the slides at the end of the presentation so you can take a closer look at what this looks like. And again, one other thing is, and this is specifically assembly language, but in comparing microcontrollers, people make the mistake of thinking that you're comparing apples to apples. It's not always apples to apples. So it's important to understand the actual instruction set that is natively supported on the microcontroller. Now, that doesn't mean that you can't get the microcontroller to do things. It's just that the things, the instructions that are natively supported, they will run in one cycle, in one clock cycle. But the instructions that aren't natively supported, you're going to have to implement in software, and that could take multiple clock cycles. So when you do a comparison between two microcontrollers, for example, if you take the Cortex M0 Plus and you compare it to the Cortex M4, you can see that the Cortex M4 supports a much larger instruction set. So even a Cortex M4 that is running at a lower clock speed could perform the M0 Plus at a higher clock speed because you're running certain operations that are native to the M4 but aren't native to the M0 Plus. However, the M4 will consume more power. So if you're looking at an implementation in which you need the native capabilities of the M4 and you do not care too much about power, perhaps it's not going to run on embedded batteries, or it's not going to be in a place where supplying power is an issue, then M4 is definitely what you should go with as opposed to the M0 Plus. But this is just putting it out there. It's a useful reference whenever you need to compare microcontrollers for optimal applications. Now, the RP2040 appears in a number of development boards, and this is a non-exhaustive list. This is just an example. We're going to be looking at the first two today. So the first one is the Raspberry Pi Pico. So this is from Raspberry Pi. It's basic. It has just the chip. It exposes your I/O ports, but it comes in at about $4, so it's easy to pick up a lot of these and prototype. And this is the development board, not the chip itself. The chip itself comes in at about $1 at retail pricing. So when you're going to embed it into your own printed circuit board, it's really affordable. The second one we're going to look at is the Arduino Nano RP2040 Connect. It's a bit of a mouthful, but every word there has a meaning. So the Nano is a form factor for Arduino. So they have different form factors. The Nano is a very specific form factor. But the Nano comes with different processors. So for example, there's a Nano 33, which comes with an NRF processor. The Nano RP2040 comes with the RP2040 processor. And the Connect in there shows that you have connectivity options, and those are the BLE, Bluetooth Low Energy, as well as Wi-Fi. The RP2040 Connect comes with other additional things that the Pico doesn't come with. It comes with an inertial measurement unit, and that's what you would call an accelerometer. It's a 6-axis accelerometer, so it's actually an accelerometer and a gyroscope. Comes with an onboard microphone, a crypto coprocessor, which you need if you're going to be doing things over Wi-Fi. But it costs about 5 times what the Pico costs for all of that. But it's useful for prototyping, especially if you need to capture sound or if you need to capture motion. Then another example is the C Xiao RP2040. It's similar to the Pico, and it comes in at about the same price point. It's about $6, a little bit under $6, but it's even smaller than the Pico. It's about thumb size, so it's about half the size of the Pico. And then there's another implementation from Arduino. Arduino are famous for their cameras, for their Raspberry Pi cameras, and they have the Pico for ML. And the Pico for ML is a Raspberry Pi Pico with onboard Bluetooth, with a microphone, with an accelerometer, with a 0.96-inch LCD display, with an initial measurement unit and a camera. And it comes in at about $30 to $40. But it's useful for tiny ML prototyping on an RP2040. So the microphone lets you prototype wake word detection using tiny ML. The accelerometer lets you prototype motion activity. The camera will let you prototype some computer vision things, all useful on low-end devices. The Bluetooth is useful for communications. So we'll start off with the Raspberry Pi Pico, which is the cheaper alternative. Again, the specs are up on the screen: dual-core ARM Cortex-M0+, 264K of internal RAM, 16 MB of flash memory, Arduino core support, and we're about to see that presently. MicroPython support, C++ toolchain. And the most important thing, of course, to do before you start working with the board is to look at the pinout diagram. And what you'll see is that there's quite a bit going on with this board. To the left and to the right, you can see the pins labeled, starting from 1 on the left and all the way to 40 on the right. The first columns out, well, let's start with the left side. You'll see a bunch of green, and green stands for general purpose input output, as well as programmable IO. Now, general purpose input output is high level, programmable IO is low level, requires a bit of assembly to get it done, but you'll still be writing that assembly from whatever language you're working in. So if you're working in MicroPython, you'll write that out in MicroPython. And if you're working in C++, you'll write that out as well in that. You'll see a bunch of black on the left, and that's your ground connector. So this particular board happens to feature 9 ground connectors, which is a lot, but there's a history to it. If you read up on the release notes of the Pico, you'll find out why there are so many of those. But it's useful because it means that you don't need to run around too much in order to find a ground connector. To the right, the first column on the right, we see some red blocks, and those are for power. So there's VBus, which is power coming from the USB. There's VSys, which is input power. So if you're going to provide power to the pins without using a USB cable, to the board itself, actually, you can provide power. And then you see number 36, which is 3V3, that's 3.3 volts out. It's 3.3 volts, maximum of 250 milliamps that components can draw from the board. And then the rest of it is all of your green, which is GPIO, except for pin number 30, which is for system control, and that's the one pin. At the very bottom, you've got debugging pins. So you've got your a ground connector as well as two other pins that can be used for debugging. Back to the left side, the second column going out from the board is, I don't know if I'll call it pink, but that's SPI, serial peripheral interface. And that SPI has, there are actually two SPI connectors, but you're able to do it multiple times. So you see SPI 0 and SPI 1. And SPI basically uses TX, RX, SCK, and SCN. But you have multiple places where you can pick that up. What really matters is that if you're working with SPI 0, then you need all the pins to utilize SPI 0. And if you're using SPI 1, make sure that all of your pins are labeled for SPI 1. So whether you take it from the left or from the right, it's really up to you, depending on what other pins you're using and what you're using them for. So that SPI, you see it on the second column from the left, and you also see it on the second column on the right, but just 4 of the pins on the right, whereas all of the pins on the left can be used for SPI. And right next to SPI is I2C. And again, you've got 2 I2C channels, 0 and 1. But again, you're able to use all of the pins on the left for I2C. And you're able to use about half of the pins on the right for I2C. And then you've got UART. Again, there are 2 of those, and UART is basically just TX and RX. But you've got it on the left, you've got 4 sets of pins that you can use for UART. The 2 at the top and the 2, 16 and 17 are UART 0. And then the remaining 4 on the left are UART 1. On the right, you've got only 1 set of pins, which is 21 and 22, that can be used for UART. Again, that's just TX and RX. So TX from this board would connect to RX on another board, and then RX on that other board would, TX on that other board would connect to RX on this board. So that's the pinout diagram. That's what you're able to do. We won't actually demonstrate anything that requires utilizing the pins, but when you purchase the Pico, you're able to choose either a pre-soldered board or one that isn't soldered. If you get one that isn't soldered, it will come with the pins, and then you can solder that on whenever you're ready. Or you can go ahead and take what isn't soldered and embed it into something else. So I'll quickly talk about the Nano as well, and then we'll jump to the IDEs. So in the previous slide, when I showed the Pico, it was pre-soldered. The Nano isn't pre-soldered. That's what I got. I had the option of getting pre-soldered or not. But you can see that the pins come along with it, and you can go ahead and solder it whenever you're ready to. One thing that you'll notice on the image here is this gold thing on the extreme right, the gold box with blocks written on it. And that's your Wi-Fi and Bluetooth radio. So that's one thing that is different from the Pico. You've got your onboard Wi-Fi and Bluetooth, but you've also got a camera as well as an inertial measurement unit. It's got similar memory to the Pico. It also has Arduino core support. It also has MicroPython support. But the Arduino boards that support MicroPython, they've got a license for something called OpenMV. And so that's what we're going to use for MicroPython programming. So the OpenMV IDE is able to deploy MicroPython onto the board so that you can go ahead and work with MicroPython. There's also a C++ tool chain as well. Yeah, and I think I've mentioned the others. The pinout diagram here is slightly different. Even the number of pins that are exposed are not exactly the same. So on the Pico, we saw 40 exposed pins. Here you've got about 30 exposed pins. So pins have already been used for things like Wi-Fi and the inertial measurement unit. So they're not available for you to utilize in your own application. Again, we've got color coding, black for ground. Notice here that we've got only 2 ground pins versus the about 7 that we had on the other side. And the power pins are in red. So on the left from the top, we've got 3.3 volts out. Further down, we've got 5 volts out. However, that 5 volts out isn't available. You've got to flip the board over and solder some connectors before you can get 5 volts out. So this is basically saying you need to intentionally enable 5-volt outputs before you can use it. And then you've got your V-in. So if you don't want to power the board via the USB, like if you've got a prototype that you've built and you've embedded, then you can power it from the V-in pin. And then we've got a green, which is for LEDs. There are 2 onboard LEDs. One just signifies that the board is running. And then there's a built-in LED. And then you've got a bunch of digital pins with the, let's probably call them the striped pins. So they're both digital and analog, as is usual with Arduino. Again, the RP2040 itself, all pins rather, that are digital can also be analog. And the difference between analog and digital pins clearly is that with digital pins, you've just got high and low states. With analog, you're able to measure a variable state. So we see those analog 1 to 7 here, and then we've got digital pins. We've got digital 13 at the top, digital 14 going all the way down to digital 21. On the right, we've got RX and TX, so that's the equivalent of UART that we had on the Pico. And then we've got D2 all the way to D12 running up. There's a reset pin. And then we've got, let's see, yellow. Yeah, so the yellow is kind of what you would use for I2C. So you've got your software clock, SDA, SCL. So that's A4, A5. You would use those for I2C. There's a the CIPO is carrier in, peripheral out. It used to be called MISO and CISO, or master and slave, but now it's carrier and peripheral. So it's carrier in, peripheral out, or carrier out, peripheral in. So those are the pins. And before we get to questions, I will just do the demos. So I will start with the Arduino IDE. And we've got the Arduino IDE. So with the Arduino IDE, there's already support, and don't worry if the IDE looks a bit different. I have got I've got a V2 version of the Arduino IDE, so don't worry if it looks a bit different. I was trying to zoom in on my code, but it's not really critical. So let's just Um, sorry, just a second. Didn't mean to change my theme. Um, oh well, we'll just try and make the best of it for now. So to start with, the IDE already supports the Raspberry Pi Pico, but you can always go and select. And all you have to do if you're working with the Pico is just type in Pico and you'll see it there. If you don't, you can go to your board manager and just find the Raspberry Pi Pico and you can work with it. I haven't connected mine, so I'll just go ahead and connect my Pico and boot it up. So I have got a brand new Pico and um, I don't know what's on it yet, but I have powered it on. And what I need to do is just go ahead and tell the IDE that I'm working with a Pico. I do believe that I have passed power into it. And what I've got here is the default Blink example from the Arduino IDE. I haven't changed anything. The board definition tells the IDE where the built-in LED is located. So I'll just go ahead and work with the code the way that we, let's see if I can zoom in again. Um, well, I'll just go ahead and first of all, verify. And what verify does is it will just check that this firmware is able to run on your specified target. Uh, it sees it as not connected. So when that happens, don't panic. With the Pico, sometimes it doesn't see it the first time, but you can always just go ahead and do a deployment. So I'll give it a second and see if it detects this. And if it doesn't, I will just go ahead and deploy it. But I know that the example code works, so no worries. And it's your standard hello world blink example. So in setup, we just set the LED built-in pin to output, and then we just loop over and we do a digital write because we're just setting high state and low state. So digital write, high and low with our standard 1 second delay. So I will do this. I will upload to Raspberry Pi Pico. Hold on. Okay. So it's completed the compilation, no errors there. I can go ahead and check. Yeah, so the board is on actually. So we've got the board in there. Yeah, and it sees the board now. Um, just doesn't see any ports. I'll just go ahead and I'll ask it to deploy. And we'll just watch out for the output window. Okay. So it's uploaded it to the board, and maybe what I should do is just show you the board here, but this is the Pico, and you can see it blinking. So that's that with setting up the Raspberry Pi Pico and using it from the Arduino IDE. So obviously you can go ahead and do whatever it is that you typically would do with an Arduino board. You can write your code normally. So I will stop the Pico and disconnect it, and I will plug in um, the Nano RP2040 Connect and start it. Okay, and all I have to do here is, so it sees it already because it's a native board. And I can do the same thing. I can go ahead and verify, but let's not waste time. Let's just deploy it onto the board and let's wait for our output. So in my experience, it takes a few minutes to compile. It might just be my system. It's a bit old, but it just takes a few minutes to compile. But I know that something is happening when I see indexing show up, so I'm not really worried. We'll just give it a bit of time to deploy to the board and then. Okay, so our compilation is complete, our upload is complete. And so this is the Nano RP2040 Connect. And recall that this has two LEDs. So the green is the power LED and it's permanently on because the board is powered. And then the orange is the onboard LED and it's flashing. So it's doing what we asked it to do. Okay, so all of that is plain and simple. For the Raspberry Pi Pico, you can also work with the C++ tool chain. I won't illustrate that now, but I do believe that I already have a video out that shows you how to set up your tool chain using either C Lion or Visual Studio Code. But I know I have articles for those, so you can check my blog for that. Okay, so that's Arduino. And next, I'm going to go back to Raspberry Pi Pico and we'll look at MicroPython. Now, for MicroPython, you need an IDE called Thonny. And if I can find it, how do we know this here? Okay. So you need an IDE called Thonny, and let me just do this just to show you. Yeah. So to get the IDE, just search the right browser for Thonny editor, and this is it. It's a free editor, so you can always just go ahead and download the Thonny IDE. I've got it downloaded, so I will start it. But before I do, I will show you how to get the Pico ready for MicroPython. So by default, it comes ready for C programming. I'll plug the Pico back in and I'll put on the power. Okay, so I've got the board back on and you can probably see it blinking. But what I need for the board to do is to show up in my file browser so that I can do something. And what I need to do is I need to flash the MicroPython firmware onto the board. So typically, if you're used to working with Python, you know that you need to install a Python interpreter on your computer. But this time around, the MicroPython is going to run on the microcontroller, which doesn't have an operating system. So the way to do it is to flash MicroPython interpreter firmware onto the board. And the way to do that is there's a reset button on the Pico. So I need to turn off the Pico, and then I need to hold the reset button and then turn the Pico back on. And when I do that, turn it back on, release it, and I'll have this new drive up here, which is this Raspberry Pi RP2. So it's a Raspberry Pi Pico. I can go in and I'll just see this, and you can always open this, and it will take you to where you can download the firmware that we're looking at. But I have it downloaded, and all I need to do is drag it onto this. Drag it onto this, and it will flash and it will reboot, and so it disappears because it's rebooted, and now it's ready for programming in MicroPython. It's that simple. So I can go ahead and start up my Thonny editor. Right, and once I've got the Thonny editor open, what I need to do is choose my interpreter down here. So besides MicroPython, there's another Python for microcontrollers called CircuitPython, but we're going with MicroPython. You can also go with a Python interpreter that is on the computer, and that means you're going to be using Thonny for desktop programming. But we're going to use it with the MicroPython, and you see that it detects a Raspberry Pi Pico is connected. And don't worry about all of these red things. All you have to do is hit stop. Okay, I'll just restart the board again. And I'll hit stop. Okay, anyways. So I'll just go ahead now and open up Blink, which is written in MicroPython, and I've got it. If I can find it. The Raspberry Pi folder. Examples, projects. So I'll go ahead and open Blink. And this time around, you see our import statement. So we're definitely working with Python here. Import machine. So this is one library that is specific to microcontrollers. And then we'll also import this utime, and then we'll define our machine pin. I'm not sure why I set it to pin 0, but we'll define our machine pin, which is our onboard LED. I think it's 26. I'm not sure why I have it as 0. And then we'll just go ahead and we will toggle the pin. So it's set to out, and then we'll toggle the pin, and then wait a minute. And when we toggle the pin, what it does is if it was high, it will be set to low. And if it was low, it will be set to high. Okay, so it's not seeing the board, so I should probably just I should do this again. Okay, this board isn't working for some reason, so just a second and I will connect another board. Okay, so I think it's seeing this board, and we can go ahead and run our script. So it will just run this, and hold on. Let power it off. Okay. Oh, I think I have an idea what's going on. I've got another editor open, so let me do a few things so I don't have problems with. Um, yeah, so I've got this OpenMV open. I think I'll just close it for now. And then save. Okay. Yeah, that's it. So the problem was I had a bunch of editors open and they're all trying to read the same place. So yeah, while we have this, let me go back to the other board then. So obviously when you work with microcontrollers, you tend to have more than one board, so you can just do a sanity check. Okay, so yeah, this happens during live demos. So connect our board, plug in power. Just bear with me, we're almost done with the whole session. Yes, someone on Facebook says these boards have a mind of their own. Right, so if I've powered it on, um, I'm not sure. Well, surprisingly, that first board worked. This one isn't working. So back to the first board. It's the second board rather. Ah. I don't have anything else running. So I'll just quit this and open it up again. Okay, so once you see this REPL, you're ready to run your code, and you can just hit run here. And let's see. Yeah, so I'm not sure why I put 0, why I made it pin 0, but ideally it should be pin 26. Stop this. Or pin 16. I'm not sure. Oh, okay. Actually, I think I know what the problem is. But I think it should be pin 26 that I should use. What I can do is save this and run it. So I'll save it to the Pico. I actually even need to save it to the Pico. I have something running on the Pico, so I'll open that. I'll open this Blinky that is on the Pico. Yeah, and it's pin 26. So I'll ask it to run, and so this is it running, and you can see it blinking. So it's pin 26, sorry, 25 actually. And then I can go ahead and stop it as well. So you'll always see feedback here. If I do something like print out for debug purposes, the printouts will appear here. So once you have this up, obviously you can go ahead and write all of your MicroPython. But the key point to remember is that you need to flash your firmware onto your board, and then you need to be sure that you've got only one editor that connects to your boards. If you've got more than one, you'll have a problem. So part of the reason that we were struggling was that we still had Arduino open, and Arduino is right into the same uh, microcontroller as the Thonny is trying to write a microcontroller. So that's the Pico. You can go ahead and program everything else afterwards. And I will stop this, turn it off, and close the editor. Close the editor. So I will then go ahead and open up OpenMV. So I'll launch OpenMV so that we can work with our Arduino. Now, I just updated OpenMV, so let's keep our fingers crossed. But basically, yeah, and OpenMV, you can again search for OpenMV, and you'll find actually OpenMV editor. So OpenMV, they make their own hardware, but if you search for the OpenMV IDE or editor, you will, yeah, so you will find the link to it. So I've got OpenMV already, which is here, and I'll just go ahead and I can close this. But first thing that we need to do is physically connect our board. So I've connected the Connect, RP2040 Connect. And then down here in the editor, I just click on this. So it says no OpenMV cams found. So what I need to do is, I don't have an OpenMV cam connected actually. What I need to do is again come back to our IDE. So with the Pico, we held down the reset button and rebooted. With the Arduino, we'll just double click on the reset button. It's not powered. So I need to turn it on actually. Turn it on back here. So it sees our board, right? And it says a board in DFU mode was detected. What would you like to do? So with the Arduino board, you need to install the latest release firmware, and that's this. Now, do not ask it to erase the internal file system unless you want to, of course, but it doesn't need to do that. Hit OK, and where did it disappear to? Okay, so like I said, new installation. I hope it's not having a bad day. So let's see. No. So I will double click to put it into the bootloader mode again, and then I will try that operation one more time. So I'll come here and it says it's found the board. I will say okay, and it's flashing the firmware. So it's by the time it's done, we will be able to work with MicroPython just like we did with the right. So it's complete and it's connected. So if you hit this, it will disconnect, and then you've got your play and your stop buttons as well. So we can go ahead and, yeah, I'll just get rid of all these. So I just want a new file actually. No, let's do this. So recall that what we did was we imported machine and then utime. I don't need to reset any sensors. I don't need to do anything with the clock. So in MicroPython, any setup that you have will appear here. I need to be sure of what my onboard pin is. So I'll just call it LED, and it is, let me do this, save myself some typing. So I will, from machine, import pin. It's the only thing I need. So this is pin, the onboard pin is 6, onboard LED. And then we'll do pin dot out. So we'll set it to be an output pin. So this is typically what you would have in your setup code block in Arduino. And then here, this is what you would have in your loop. And so what we need is LED. So the first time around you saw toggle, but you can also use LED.on, and that just sets it to on, and then utime.sleep. And you can use sleep, which is in seconds. You can do sleep milliseconds, sleep microseconds. That's MicroPython for you. So sleep for 1 second, and then turn it off, and then sleep for 1 second again. And if I have no typos, I should be able to just hit run here, and it starts to run. And if I can find my StreamYard window, and this is it blinking again, and then I can stop it whenever I'm ready, and it stops, and I can start it again. So that's MicroPython running on your Arduino board. And from this point, you can go ahead and write whatever it is that you want to write. So we're almost at the top of the hour. I will take questions. So feel free to write any questions that you have. I will see them come up in the comments, and I will answer them. And if there are no questions, I will just thank everyone for coming, and I will drop a link to my slides, and I will also update the video on YouTube with a link to the slides at the end. Okay, I don't see any questions coming up. So it looks like, right, how do we get these boards? So there are a few boards that are available to give out. I just need you to take a course, but I will post about what you need to do by next weekend. Probably also just host a small meetup about it, but I can send you a board. You just need to take a course and prove to me that you're ready to use the board. So it's just a bit of give and take, but I can send out free boards once you take a course. So keep your eyes on whatever space you are. So I see you on Facebook, so keep your eyes on the group. If you're on YouTube, I will also post about it. But in about a week, I will tell you how you can get these boards. So obviously, you can purchase the boards directly from any of your favorite vendors, but I will also be giving out the Nano RP2040 Connect so that you can try your hands on some tiny ML applications. Okay, so I will assume that there are no more questions, and thank you to everyone for tuning in. Enjoy the rest of your day.